It's beautiful, isn't it? An incredibly responsive rotary encoder that's controlling a 16-bit indicator display. Not just that, but there's 3 buttons which instantly go to a particular intensity. This is precisely where we ended on the last episode, where we leveraged the analog to digital conversion peripheral of the PIC microcontroller to interpret those various different button signals into one pin. These buttons generate a different voltage, which is interpreted by the microcontroller to a single digital value, and that value is an intensity level for illumination. But you're probably already seeing the problem. The changes in intensity level is quite abrupt. And practically speaking, those changes could be quite unpleasant. We need to smooth them out. So we can turn these changes into something more like this. And those smoother changes need to be automatically timed. So if you remember from some of the previous episodes, we're going to bring back the use of our timers. But before we get to that, we're going to go on a small tangent. Not because the topic of this tangent is directly related to the smoothness of intensity. Actually, what we're going to learn on this tangent is going to help us out. And that tangent has to do with resets. See, right now, when we reset this device, it resets almost instantly and just jumps right back into operation. It even does that from a cold power start. Now, right now, the code is working really well, which is why it does that. But occasionally, code doesn't work as we intend it to. Sometimes our code might inadvertently cause a stack overflow or underflow, or worse yet, that watchdog timer reset. And in each of those scenarios, the microcontroller would simply reset and continue running. But there is a way to determine what caused the reset, which is extremely helpful when figuring out what went wrong in order to solve the problem. A little bit lower down in the datasheet, there's a table which helps us determine the cause of a reset. You can see all the conditions on the right side, from watchdog timer to mclear reset to stack underflow and memory violation reset, and a bunch of flags listed on top and their status from 0, 1, or unchanged. These flags are part of 2 registers, PCON1 and PCON0. So one thing that we can do is write some code that as the device starts up, it will display the status of those 2 registers, wait a little bit, and then continue on its way. And during that wait, we can view the status of those registers to determine why the last reset was caused. And depending on the pattern that gets displayed, we get some hints as to where to go to solve our problem. So you can see why we're going to need a timer to hold that information on the indicator display before it continues as normal. But we're going to need more than a timer. We're actually going to need to define a system state. And by system state, I'm referring to this thing called a finite state machine. Now, we can spend a whole episode talking about finite state machines. We're clearly not going to do that, but I do recommend brushing up on the topic because A, it's really interesting, for some of us at least, but it's also really powerful when we're working with embedded microcontrollers. So without going into the details, we are going to be building a finite state machine, and the first thing that we need is a state machine register. So in our code, we'll create a general purpose register to define that system state. As our microcontroller gets started up, we're going to create code that's going to cause it to display the power-up flags on the indicator. It needs to hold it there for a certain amount of time. That hold is known as a system state. After the time has elapsed, it will then proceed to the next system state, which is normal operation. And we need a register to remember which state we're in. That's what this register does. And to determine when to proceed to the next state, we're going to use an interrupt on timer 0. Currently, we don't have an interrupt enabled for timer 0, so we're going to put the code in to do just that. The interrupt flag for timer 0 is bit 5 on the PIE 0 interrupt register. Now, to help reduce all the things that can go wrong while we're doing all this coding, we're going to temporarily disable all of the other interrupts except for the serial port interrupt, because that serial port interrupt is necessary for us to get the information out onto the indicator display. And if we remember, that serial port interrupt is bit 1 of the PIE 1 interrupt register. So we'll make sure that's enabled and comment out all the rest. Then we can insert the handler, and all that handler is going to do is read the system state register and call a certain portion of the program based on the value in that register. So if you remember from the last episode, we used this call W instruction as a table lookup. It uses whatever value is in that register and interprets it as an address. And it then goes to that address and then does something based on the instructions at that address. And our code right now is pointing to a location in program page 2. So let's go to that location in memory and create the code that's going to determine the state actions. Let's pop this code in after the main program, but before our button lookup. And I'm going to use the program address of 240. And the code here will display the power-up flags. However, we're going to insert some temporary code that's just going to set the intensity to maximum, just to test if this works. Then, just as we complete the initialization process, that system state is the first one that gets activated. And then as that state completes, we need to configure the next state that the system must go into. So we'll configure the state register with a different address, the system state that returns everything to idle. Then perhaps up here at address 220, I'll create the code for that state. And all we're going to do is configure the indicator to minimum. And then we'll change the system state register once again to idle. Clearing the register, we can set the address to 00. But remember, we're in program page 2, so that's actually address 200. So up here, we'll put the code for our idle state, which simply returns and does nothing. So let's program this and see if this works. When we hit the reset, look at that. You can see that it jumped up to maximum and then quickly jumped back to minimum. So it looks like it's working, but the time spent in that state is awfully short. We need to extend it. Scrolling up to the top comments in our code, we can see that timer 0 is currently configured to have an output period of 250 milliseconds. Now we certainly want to change that, but it turns out that if we adjust all the values so that we maximize the timer countdown and then maximize the pre and post scalars, we're still not going to achieve a reasonable time for a human to interpret that indicator output. And that's because the input clock source is set at 500 kilohertz. Which, if you look in the datasheet, is the medium frequency internal clock source. Lucky for us, in a previous episode, we discovered that there is a much slower 31 kilohertz clock source that we can use. That's this one right here, the low frequency internal oscillator. And as we discussed in that previous episode, the low frequency internal clock source is not all that precise. But honestly, whether this is 3.8 seconds or 3.9 seconds, I don't think it matters. So let's first put in some comments that will describe the configuration of the timer 0 slow speed. And if we use this configuration, we should get an output period of about 4 seconds. That is perfect. While we're at it, I'm going to adjust the timer 0 fast settings to give us an output period of about 50 milliseconds. Why did I choose 50 milliseconds? We'll find out soon. So now let's add a couple of constants, which will allow us to configure timer 0 with the 1 to 8 post scalar and a 1 to 64 pre-scalar with the 31 kilohertz input clock. At that speed, a count of 245 will give us the approximate 4-second delay. And here's the fast constant, which changes our pre-scalar to 32 and the input clock source to 500 kilohertz, and the count limit of 98, which, as we just discussed, gives us the period of 50 milliseconds. And down here where we initialize a timer, we'll use our shiny new constants. Then in our display powerup flag state, I need to adjust the timer speed to our slow constant. And then in the next state, when we return to idle, we have to switch it back to the fast constant. Let's assemble and program, and let's test it out. Hit the reset, and oh, look at that. It holds for about 4 seconds and returns down to normal. That is perfect, and you can actually see the speed change of timer 0 by the LEDs that we have in place on the board. Remember, this upper LED right here is connected to the hardware out of timer 0. And you can see that LED slow down, and after 4 seconds, speed up. But you're probably noticing something odd here. That second LED is also blinking, and it's blinking at the same rate as the top LED. And that second LED happens to be a visual indicator of timer 1. We can confirm that in our code. And there it is, the timer 1 rollover is inverting bit 4 of latch C, which is connected to that LED. But we disabled all of the timer 1 interrupts earlier, didn't we? That's what these commented lines should be doing. We disabled all of the other interrupts. But curiously, the rotary encoder still works. Kind of. It's not actually doing what it's supposed to, but it is receiving a signal. Now it turns out this was due to a little mistake I made a long time ago when we first designed the interrupt handlers. You see, by commenting out these lines, we're not actually disabling the interrupts. The flags that change when an interrupt occurs still happens. All we thought we were doing is disabling the actions. But it turns out we weren't really doing that very well either. See, by commenting these lines, the peripheral interrupt enable registers never got enabled, but our interrupt vector over here will still take action on those flags. The only thing is, the microcontroller won't activate that interrupt based on those flags. However, we still have 2 interrupts activated, the timer 0 and the serial port. So it turned out that whenever timer 0 interrupt was activated, it went to this interrupt vector and it processed the timer 0 interrupt, but it's also processing the rest of them. It just processed them at the incorrect time, which is why the rotary encoder doesn't really function as expected. See, the right thing to do is before calling each and every handler, we need to test if that associated enable flag is set. And if it's not set, don't call the handler. So let's make a few changes here. First, I'm going to move this block of code so the order makes a little bit more sense. And then rather than testing the interrupt flag directly, we need to AND it with the enable flag register, and then test the result of that operation. That way, the interrupt is only actioned if the interrupt occurred and we've enabled the interrupt. The rest of these can be changed in a similar fashion. Now when we assemble and program, the interrupts are properly disabled. Notice the timer 1 LED is not blinking now. Okay, so now that the startup state progression is working as expected, we can finally work on the output of the power control flags. First thing we'll do is we'll create a new general purpose register to hold that data. Then we'll remove the temporary code we put in the power up state and replace it with some code that's going to isolate one flag in the PCON1 register and store it in a common bank register. That flag is right here, bit 1 in the power control register 1. It's the memory violation flag. And interestingly, it's the only useful bit in this entire register, so we only need that one. So over here, we store that away in the common bank register, and then we're going to move it from bit 1 to bit 5. Stay with me, you'll see why we're doing this. Now we're going to create a mask to isolate all the bits in the power control register 0 except bit 5, apply that mask and store it in the working register, and then combine it with bit 5 in the common bank register using the inclusive OR instruction. And the reason we did that is because in the power control register 0, bit 5 is the only one that's unused. So we combined the flags in 2 registers into 1, and we're actually not losing any information. Why they organized it like this? Regardless, it makes it easier for us to display all that information in a single 8-bit register. Okay, we're not quite done yet because there's something that really messed me up when I was going through testing. And that bit was right here, where it says that hardware will change the corresponding register bit during the reset process, which is exactly what we expect. And then it says software may reset the bit to the inactive state after restart. Hardware will not reset the bit, which is what I didn't expect. So if a certain condition caused any of these bits to activate, it would show up in the power control registers on the next reset. But if you then reset it again, it would appear as if the same condition was still there because we never reset the bit. And that's what this statement warns you about. But of course, I didn't heed the warning until a long time after. So in our code, right after we've captured PCON1 to the common bank register, we're going to set that memory violation flag back to its default state. And then do the same thing with the power control register 1 by setting all the flags to their default state. So now that we have the power control registers all bundled into a single 8-bit value, we can now output it to our indicator. But the indication subroutine that we have right now won't work. See, this indication subroutine is intended to take a binary value and display it as a single bit in our indicator to indicate the level of illumination. But that's not what we're trying to do now. We're trying to display an actual value on the indicator display. So we're not going to be able to use this. We'll have to create a new subroutine to display a single 8-bit byte. And our new indicator byte subroutine will take the value in GPR24, which is the indicator display data, and send it to the serial buffer. But it's going to do so ensuring that it's only sending a single 8-bit output. Now this is imperfect. As you know, we have a 16-bit output, and if we only send a single 8-bit value, it's going to push everything over by 8 bits. So the single bit that's lit up here will end up getting pushed over to bit position 8. So yeah, it's not perfect, but the steps required to fix this are actually quite complicated, and I didn't want to really get into it right now. I thought, we'll just deal with it. So if we assemble and program this, on reset, that first bit got pushed over to 8 as expected, but now we have a pattern. And that pattern should match this register over here, with the exception that this bit 1 over here has been moved over to bit 5 over here. So let's take a closer look at that pattern. We can see bits 0, 1, 2, 4, 5 are on. And so looking at the datasheet, that means that BOR, POR, RI, RWDT, and remember, MEMV are all on. So looking at the description of MV, if it's on, it says no memory reset occurred. That's a good thing. A BOR that is on says no brownout reset occurred. A POR that is on says no power on reset occurred. An RI that it's on says a reset instruction has not been executed. I know, it confused the heck out of me as well. Anytime you see a flag that's on, intuitively I want to say that it has been done, but it just means you gotta read the datasheet very carefully. Moving a bit further, a 1 on the watchdog reset flag means that a watchdog reset has not occurred. 6 and 7 were off, however, and so 0 on both of these says that a stack underflow or overflow has not occurred, just to add to some of your existing confusion. And going back to bit 3, which was also off, a 0 says that an M-clear reset has occurred. Aha, so this was the cause of our last reset. The M-clear is connected to a pin on the microcontroller, which happens to be connected to this button right here. So every time I press that button, I am inducing an M-clear reset. And so bit 3 turns off, indicating that that's exactly what happened. Just to test this, I'm going to do a hard power reset instead of using the M-clear. Now look at the configuration. It's bit 2, 3, 4, and 5 that are on. Going back to the datasheet, we know that bit 5 equates to bit 1 in the power control register, so the memory violation flag is still 1, which means no memory violation has occurred. We know that bits 7 and 6 are still 0, so no stack overflow or underflow. Bit 4 was on, so no watchdog timer overflow. Bit 3 was on, so an M-clear reset has not occurred. Bit 2 was on as well, so a reset instruction had not been executed. But bit 1 and bit 0 were both off, indicating a power on reset had occurred and a brownout reset had occurred. Which makes sense because we did a hard power on reset, and so the power on reset would have occurred. Now the brownout reset confuses me a little bit because it suggests that a brownout reset has occurred. I looked into the datasheet and I found that by default the brownout reset capability is enabled. I honestly haven't done a lot of research into this, and quite frankly, I couldn't get the thing to reset without the brownout reset. So I'm thinking this is normal. If you know better, please let me know. All right, so now that this is working, let's get the rest of the functionality back again. And we can do that by adding some code in the return to idle state, which will simply clear any interrupt flags that may have triggered, and then adjust all of our interrupt enable registers. Then we can go back to the lines that we commented in the initialization section and simply get rid of them. Now, if we assemble and program, we can see the startup powerup flags, and once they go away, everything works as normal. And now finally we can focus on the topic that this entire episode was about, smoothing out those abrupt intensity changes. And by now, hopefully you've picked up on why we wanted to do that little tangent to begin with. These abrupt intensity changes require timing to smooth them out. And we just configured a bunch of system states and utilized timer 0 to move between those system states. And we defined 2 different speeds in our timer 0 delay. One we've used already, the 4 seconds. And the other one, well, we're going to use that now. And that's why I set it to 50 milliseconds, because I thought that would be an appropriate time for the transition to take place. Not the entire transition, mind you, but the transition between each intensity level. So to move from this intensity to maximum intensity, it's about 6 stages. And to go from maximum to minimum, for example, is a full 15 stages. And each of those stages should take 50 milliseconds to complete. But that also means I'm going to need 2 pointers. One to point to what the target intensity is, and another to point to what the current intensity is. So let's create another general purpose register to hold our intensity current. As we begin the initialization process, we'll clear that intensity current so it starts off at 0. And then in our button release handler, I'm going to remove the line where we call the indication. Don't forget to adjust the branch lines. See, whenever our button is released now, the target intensity will change to the new value, but the current intensity will remain where it is. And we don't want to call the indication process right now. We need to wait a certain amount of time and then adjust the current so that it will catch up to the target. And that can be done in our idle state. Here we'll capture the current intensity to the working register and then find the difference between the current intensity and the target intensity. And if that difference is 0, we don't need to do anything. If the current is greater than the target, then we decrement the current by 1. However, if the current is less than target, then we increment the current by 1. And only then do we call the indication subroutine. And remember, this state is only called when timer 0 overflows, which happens over here in the timer 0 rollover. our system state will be set to idle, and that's the code that it's going to call. And the output period for timer 0 is 50 milliseconds. So that means the current intensity should catch up to the target intensity one step at a time, each step taking 50 milliseconds. The final thing that needs to be changed is in our send serial data subroutine. Rather than using the target intensity here, we need to use the current intensity. If we assemble and program that, now if we go from minimum to maximum intensity, look at that. Nice, smooth transitions. Oh, it's lovely. It even works on the rotary encoder. It now appears to have a maximum speed, so spinning it fast has no effect. I don't actually think I like that. I want the rotary encoder to be instant. So we can make that change in the rotary encoder handler. So on any rotary encoder action, rather than adding the increment to the target intensity, I'm going to add it to the current intensity. And all the tests to make sure that it hadn't surpassed its bounds needs to be tested on the current rather than the target. And then finally, we want to make sure that the target and current are the exact same value. And we can do that by copying the current into the target. Assembling and programming. The button press is smooth and the rotary is nice and fast. Oh, those transitions are nice and smooth. I like it, but I don't love it yet. See, what I'd really like is to use this button as kind of a toggle button, which means it would toggle between 0 and the last intensity, whatever it was. So obviously, if we want to remember the last intensity, we'll need a register to do that. And then as our microprocessor is initialized, I'd like that initial value to be 50% of maximum. And we can do that with a single right shift. Remember, right shifting any value divides it by 2. So right shifting 100% equals 50%. And then we'll go to all the places where we make changes. Let's start with the rotary encoder. We want that rotary encoder action to be instant and also set the last intensity. Next, let's go up to the button release handler. Now this is where it's going to get a little complicated. When we release that button, we need to do a few tests. The first test is to see if switch 0 was the one that was pressed. And if it was, we're going to skip the next line. So let's insert the line we're going to skip, noting that something other than switch 0 was released. Then we need to test if the current intensity is at 0. So we'll capture that register and test it. And if it's not 0, we're going to skip this next line. Because if that's true, we want to set it to 0. So we'll set the target to minimum and then branch forward because we're done. But if the current intensity was 0, we now need to set it to the last intensity. So we'll capture the last intensity register, and then we need to test it again if it's 0. Because if we don't, we might end up toggling between 0 and 0, and that can be really painful. So if the last intensity was actually 0, I'm going to artificially increment it by 1, so we're just toggling between 0 and 1. But if that's not the case, we'll take the last intensity and use it as the next target. Let's adjust the branch comment here to reflect that that's the scenario where we're actually going to retrieve the intensity last. I still don't have a value, so we're going to leave that branch value empty. Now we'll consider the scenario where switch 0 was not pressed and was actually one of the other ones. In that situation, we'll take the target intensity and also store it as the last intensity. Now we can actually enter in all the values for our branches. And now finally, we have to adjust the long button press action. Currently, it brings everything back to 0, but let's temporarily replace that with something more interesting. How about we cause a system reset? So let's comment out the indication line and introduce a reset. Assemble and program. On a fresh start, switch 0 should bring it to 50% intensity. And sure enough, it's exactly what happens. And if we toggle it, it goes back and forth. Let's push a different button, which brings it to intensity number 2, and then try toggling it. And look at that. It goes back and forth between 0 to 2. Let's use our rotary encoder to go one less than maximum. So this is going to be intensity 14. Now we toggle it. And look at that. Back and forth between the last intensity. Oh, that works so well. Let's do the long press. Reset. And look at the pattern, 0, 1, 3, 4, 5. And sure enough, if bit 2 on the power-up flags is 0, that means a reset instruction has been executed. I love what we did today. Not only did we create code that allows us to interpret those power-up flags, we created a finite state machine which pauses so we have enough time to interpret those power-up flags and those transitions. Oh, the transitions, they're so nice. The illumination changes when we get there are going to be so smooth like butter. So, I'll see you next time.